Hello and welcome to PyData Global 2021. My name is Rosa. I'm going to be the host of this workshop. So the workshop we're going to have right now is Introduction to Distance Metric Learning by Dor Kedem. Dor Kedem is currently managing a data science and engineering team at ING Bank in Amsterdam. Between his tasks, we can mention financial criminal risk mitigation, money laundering risk detection, and supports the analytics team to make the bank more safely compliant. Within nearly 2 decades of experience working in IT, big data applications, and data science, Dor would present an introduction on distance metric learning, and is a topic that he has researched and used a lot within a professional setup. Okay, without further, I give you all as yours, the stage is yours, Dor, and shine.
Thank you, Rosa, and thanks to everyone who's come and attended. Maybe before we really get started with the talk, a bit of logistics to kind of position the way that we can interact. I think that these tutorials are a bit longer and they're at a Zoom meeting rather than as a webinar. So I do encourage a bit more engagement. The way that I think works well is to join the conversation on Slack. Basically, there is a forum dedicated called Introduction to Distance Metric Learning. Join it, say hello, look at some of the things that people already posted. For example, the link to a notebook is already there. Check out the notebook. So during this tutorial, we will go both through this presentation and another notebook that I prepared. My advice to you is to go through the notebook somewhere around midway of the talk. We will also go through this together. After the talk, I'll also be available on GatherTown. You can see my avatar here. I did my best to match my other avatar on Slack. I will find a seat. I'll also post it on Slack, and then you can have that conversation follow up. I'll still respond on Slack channel, so if there were questions that I missed, I'll be able to pick up. Or if I entirely missed all of these channels, you can reach out to me on LinkedIn. Just let me know that you came from this talk, and then we'll be able to cover this. And I think with that, we can get started. A little bit about the topic at hand, which is an introduction to distance metric learning. A little bit about me, as Rosa was mentioning, data science and engineering manager in ING. If you're interested really about what the kind of work that we do in the group, it's really about topics like outlier detection, representation learning, graph, and entity resolution. As I mentioned before, Fritz, about an hour and a half ago, gave a talk about this topic of entity resolution. Do check it out. And as for me, my career spanned nearly 2 decades, both as software development and data scientist, sort of machine learning engineer, building ETL processes. And I'll be happy to converse on any of those, right? Be it topics like security, banking use cases, machine learning, and all the way to some of my hobbies, which are board games, professional wrestling, and great cheesecakes in Amsterdam. And if you're interested in joining us, do check out ing.jobs. Our topic today is a bit ambitious, let's say. I think we have about 85 minutes right now, and we will try to cover a few, let's say, key fundamental topics, but also get to the point where you feel comfortable to try and apply this in your domain and setup. So we will go through really from the very basic, right? What's a metric, a distance function, and metric learning. We will dive into what does it mean to actually learn a distance. It sounds a bit counterintuitive, but we will dive into this. We'll look into related fields like manifold learning. We will learn how do metric learning loss functions look different than, let's say, supervised, other supervised classification learning loss functions. And we will apply this in practice. So we have a really interesting data set to kind of experiment with, and hopefully it will be fun. So let's dive into this. when I started looking into this talk, I started looking into the definition of metrics. And to be fair, as English isn't my first language, it was a bit tricky for me to fully understand what a metric is, or the difference between a metric and a distance initially. But I think this definition from Wiktionary is actually a very good one. And that's basically a mean of deriving a quantitative measurement or an approximation for things that are otherwise qualitative phenomena. And a couple of really, let's say, cool standard metrics that we're talking about is, let's say, this standard meter from roughly the 1800s, and the standard kilogram, which is stored in France. And you can think about, let's say, the standard meter, right, as a quantitative way to measure how far or close things are, right? So if I'm hungry for cheesecake and I want to go to my close, let's say, cheesecake bakery, I might be hungry and I feel it's far, but my wife thinks it's near. The meter gives us an ability to actually quantify how far is the cheesecake bakery from my home. The thing is that distances and so the difference between a metric and a distance, I think that they're quite synonyms. So metric is basically trying to estimate how similar or dissimilar things are, and distances are really trying to measure the dissimilarity part. So let's say apologies. Yeah, apologies. 1 second, guys. I have a bit of a noise from my side. Yeah. So during this talk, I'm going to use distances and metrics interchangeably. Basically, you can think about other ways that we use metrics in machine learning, such as, let's say, accuracy, which basically tries to measure how close is a prediction from an actual label. And I think during this talk, I'll mainly start to focus on the term distance, because I think distance is a little bit more intuitive. And why distances and metrics are important is, think about it this way. If we would have had some sort of a magic ball that could quantify for any two samples, right, whether they are semantically similar or dissimilar, then a lot of the, let's say, core machine learning challenges that we know of today would be trivial. So, for example, think about classification problems, right? So if you had a perfect way to determine if an image is more similar to a dog or a cat, then given a new image, I can tell you whether this is a dog or a cat. If you had a perfect way to, let's say, measure similarity between, let's say, songs or music, then, let's say, based on my own personal taste, I would be able to cluster and categorize and segment different areas of music so that I could know that, well, this segment of music I like more, this segment of music I like less, and we build my own radio station. Recommendation system, you know, if I really enjoyed a movie, if I could find a similar movie to that, right, I'll be able to stay engaged on your platform. And in general, when you think about it, right, the power of this comes from the fact that we have a lot of very good distance-based algorithms in machine learning. So K nearest neighbors, K-means, just a couple of examples, right? They're all working well, provided that the distances that you are measuring are representative of the domain that you are interested in. So if we talk about, so now we understand, let's say, why having a distance that is a representative of the, let's say, semantic similarity is important. let's try to dive into what exactly do we do when we talk about metric learning. So in metric learning, I took these definitions from Wikipedia. So you can see that similarity learning is an area of supervised machine learning. And that metric learning is the task of basically learning a distance function over object. So when I read this in the Wikipedia page, I was asking myself two main questions. Number one, why is learning a similarity a supervised task? Right? I mean, I don't know, if I have a cup and a bowl, right? Like, I can just tell they are dissimilar, right? Like, why is this a supervised task? And the second one that isn't coming too trivial to me is, what does it mean to learn a distance? And we will try to tackle both of these questions in this talk. By the way, I see that in the chat there are some activities. Just make sure that you're also reaching out to Slack so that I'll be able to answer those. I see that one of them was on board game, so I hope that this was fun. All right, so let's tackle the first one, right? Why is learning similarity a supervised learning approach? So if we look into these three images, right, we have, I think, two images of Barack Obama and one of Macron. And basically, if we would try to, let's say, build a system that tries to verify faces, right? So given a person is another image of that same person belong to that person or not? Like, basically, if I have a system of my photos and photos of someone else, I wanted to say that all the photos of mine are together in one cluster, let's say, while photos of someone else, let's say of my wife, are in a different cluster. Then we would want to have a distance function where, let's say, the distance between this photo of Obama and Macron is greater than the distance between this photo of Obama and this photo of Obama, right? The thing is, what happened if my task isn't about trying to detect faces, but about trying to detect the rotation of a face? I don't know, suppose that I have a crazy idea about trying to put faces of individuals on top of Iron Man suits. And I have different kind of models for Iron Man that is rotated in its angle, and I want to know which one fits one. I mean, I don't know why would anyone do that, but if we try to, let's say, detect the rotation of a face, right, then it could be that these two faces would be closer than these two faces. And that's why when you are talking about similarity, similarity in essence is a supervised question. So based on the task that you are trying to answer, you could try and learn different kind of distances that would encapsulate the semantic meaning that you are looking for. I will give it a chance for a question in a second. I just wanted to dive a little bit into the second question, which is about distances and learning at distances. So what exactly does distances mean? So if you go to, I think, to look for the mathematical definition of a distance or a metric, which you see they use it interchangeably, you see that it's basically a mathematical function that, let's say, given two items, provides a number. And that function needs to satisfy these certain rules. So number one is coincidence. It's quite straightforward. So if we talk about the distance from my house to anywhere else is 0, then that anywhere else, let's say that anywhere else is x, is my house, right? If we talk about symmetry, so the distance between my house and the cheesecake bakery is the same as the distance between the cheesecake bakery and my house. Non-negativity, I can't have a negative distance between my house and the cheesecake bakery. It just doesn't work. And the triangle inequality. So if I want to get to my cheesecake bakery, I can't get faster if I try to, I don't know, go through my supermarket first. If I try to go directly to the cheesecake factory, to the cheesecake bakery, that should be the fastest. And we already know of, let's say, a couple of, I think, very well-known distances that you're familiar. I think the Euclidean distance is something that I think most of us learned in junior high with the Pythagoras distance sentence, and the Manhattan distance is quite trivial as well. It's about basically we call it the L1 distance in machine learning, and that's basically the absolute distance, the absolute value of the differences of the coordinates. So you can see those couple of examples here. Now these distances are very well known, but we can't really learn anything. I mean, the distance between 0, 0, and 4, 3, the Euclidean distance between them is always 5, right? These are what's called non-parameterized distances. But there are a different set of distances that come with parameters, and that we are able to actually learn these parameters to better fit our problem. And I think for our first question that I'm asking you, and then I'll have a chance to look into the questions that we had on Slack, I have this question for you. So there is a parameterized distance that tries to combine both the Euclidean distance, when this parameter of this distance is 2, and the Manhattan distance, when this parameter value is 1. Do you know what it's called? I'm looking into the chat as well. Yeah, I see Vladimir already gave the right answer. Yeah. This is the Minkowski distance. That is correct. And this is an example for a parameterized distance where you provide one parameter. In this case, that's P. And the distance is calculated in the following formula. You can see that basically when P equals 1, then it just becomes the difference in absolute value of the coordinates, where the P is 2. Then it becomes the square root of the square value of the coordinates differences. So good of Vladimir. So maybe as a follow-up question, the Minkowski distance is only defined for P greater than 1. Does anyone know why? Yes, exactly. I think Tom wrote that as well. He says triangular inequality, and I see Risika also answered that question. By the way, Felipe asked about the third definition, that the definition is certainly not fixed here about the triangle inequality. Sometimes there would be cases where intermediate point y would diminish the distance between x and y. If so, then that would not be a valid distance. That would not be considered a valid distance or a metric. It's true that there are such functions, but then that doesn't constitute a metric. All right, cool stuff. And just so we can kind of go to the notebook as well, and of course that my kernel restarted as we had this conversation. And by the way, let me know if you can't see it. I'll increase a bit the font size. Great. If you're interested in trying out different distance metrics, then in sklearn neighbors, there is this function over here where you can try out, how does the Euclidean distance or the Manhattan distance play out on different points. And it even has the Minkowski distance. And so basically, how does the Minkowski distance value change for different P value? All right, so now I think we can dive into some more interesting stuff, because here, as we said, there's only one parameter that we can try to optimize, which is P, right? But if we want to think about I see there is Olga asked about link to notebook. It's in the, thanks, Jeremy. So if we talk about, let's say, a different set of parameterized distance matrices, we have to talk about this guy, where I think someone has already answered Kranti. Apologies if I mispronounce your name, Kranti. Already answered during the chat. This is Prasanta Sandra Mahalanobis. He is indeed one of the leading statisticians in the, I think, 1930s. I think in India, indeed, the National Statistics Day was inspired by him, and it's celebrated on his birthday. And he came out with this unique, let's say, distance function. So if we look at the Euclidean distance, which could be written out the following, right? Where basically, if this is the center, then everything that's in this circle, or sorry, that is on the border of the circle has the same distance. So a distance from here to here, it's the same as the distance from here to here, or the same as the distance from here to here. That's what's called the unit distance. Well, in the Mahalanobis distance, he proposed putting a matrix over here as a transformation between those two differences of the vectors. And what's unique about this, you can try it out. First try with the identity matrix, then start changing the values there. You will see that what you find is that there are different. You could get to a transformation where, let's say, the distance between here and here is the same as the distance between here and here. And when you think about this intuitively, so what Mahalanobis tried to do was he tried to basically define what could be a distance between a point and a distribution. So if, let's say, we find a point somewhere here, is this a part of this distribution or not? And in order to do that, he set M to be the inverse of the covariance matrix. Now, another bonus. Another bonus question. There is another very common unsupervised algorithm that uses the inverse of the covariance matrix. Does anyone know which one is it? SVD? Yeah, that's correct. PCA. Indeed, that was the answer I was looking for. There is a very strong alignment between PCA and the Mahalanobis distance. I'll show this in a bit, but just so we can kind of showcase a little bit how does the Mahalanobis distance look like. So in this code, I basically draw an ellipsoid and the figure, so you can see it. I generate some data set with, let's say, this is the mu and this is the scale of those data. You can see it over here. So this is these are a set of data points from this distribution. I also added this point and this point. And what you see, I've generated two types of distances. So first, the Euclidean distance between mu, which is this triangle, and the inlier, which is the square. So you see that the Euclidean distance from this triangle to the square is much bigger than the distance between the triangle and the outlier. But if you're taking this data and you're trying to learn the Mahalanobis distance with the same function, you find that actually the distance between this and the inlier is much less than the distance between this and the outlier. And what I drew here in fuchsia is basically the 3-unit distance. So the distance between here and here is 3, but also the distance between here and here is 3. So you really have a chance to kind of experiment and play around with this, again, with the same Mahalanobis distance metric Mahalanobis function. So you can try it out. I'll dive in. I'll show in a second why does it resemble PCA, but that's a very good answer. Okay, so we learned that basically using the inverse of a covariance matrix is a good idea, right? It gives you a good unsupervised approach. But we talked about it that metric learning is a supervised problem, and we want to maybe learn a different kind of M, an M that fits our problem. So maybe this is a trickier question. Do you know which kind of m's are required for the metrics to be well defined? For the distance metric to be well defined, and I'll try to assist. We said that every distance, symmetrical is a good idea, but it's not that. We said that every distance has to be non-negative, right? So it can't be to create a distance that is negative. Yeah, exactly. I think Tom gets that, and I see a lot of people mention that now as well. Marek and Antonella, great. So indeed, there is this definition which is called positive semi-definite, which quite literally means that, you know, for every x vector, x transpose mx is greater or equals 0. This is literally the definition. Now, I don't know how much do you guys remember your metrics cookbook, but for positive semi-definites, if you don't remember, by the way, there's a link to this in the notebook in page 51. There is this really cool property for positive semi-definite matrices that there is an invertible matrix L such that L transpose L is M. So now there's a bit of a math alert. I don't have my my horn with me. We're going to do 3 lines of math and solving. So we started with this, which is the Mahalanobis distance between x and y. We're replacing m with this term over here. We are saying the transpose of the, you know, basically the transpose of the multiplier is the multiplier of the transpose. So L goes inside here, and then we basically transpose the entire thing. And we're bringing L inside of these parentheses and also inside of here. So bonus question, can anyone try to describe what this term is? Yeah, I think Cruz said something. It is an L2 distance. It is the L2 distance, or the Euclidean distance, between, yeah. Sorry, I'm losing my screen. Yeah. It is the Euclidean distance between Lx and Ly. And when I first saw that, I thought to myself, wow, this is beautiful, right? Because what happened here, right? We started by trying to learn a distance, right? We tried to learn what is the m, let's say an m that is a good fit for us. But instead of learning a distance, we are learning a transformation, right? A transformation where the Euclidean distance makes sense. So for the rest of the talk, right? And I think this is, you should listen to Drake on this one. Instead of, when you talk about metric learning, you talk about what is the meaningful, you know, you're trying to learn a meaningful distance function in the original space. What you are trying to learn here is a meaningful transformation, so that the Euclidean space, or later when we talk about this, it could also be the cosine distance or L1 distance. But in this case, right, you're learning a meaningful transformation, so the Euclidean distance is meaningful in the transformed feature space. And I think that's is inverse guaranteed. That is part of the definition of the positive semi-definite. Indeed. All right. So if we kind of go back to the notebook, I promised you that basically the Mahalanobis distance, right? So if we saw that that's feasible for any matrix, it's also feasible for the Mahalanobis matrix. I see there is a very lively conversation in the chat. I'm minimizing it for my attention, but I'll get back to it in a second. So regarding the transformation, so for those of you who's used PCA, I don't know how much you've noticed this, but there is a parameter called whiten. And the idea behind whitening of PCA is basically transform the signal into a white noise. But what it really does is it basically transform. So if in PCA you're transforming your data in a way that creates the most variance, what whiten does is it transforms your data with the L that is the L from the Mahalanobis matrix, from the inverse covariance matrix. And you can see it here in the, I took the same data set and just applied basically once the regular PCA and once the whitened PCA. So you see it here, once with whitened false and once with whitened true. And you see that basically, so this is, if we look again at our original data, it was right here. So this was our original data set, right? After you do PCA, you get something like this because you basically rotate the axes based on the most inverse. And after you do whiten, you get something like this. So you basically transformed the original data to the space where this point is actually getting closer than this one in the Euclidean space. And to prove it to you, right? So if I do a distance, what is the distance in the Euclidean space when whiten is true? You get the distance from the to the inlier is 2.52, and the distance to the outlier is 499, which is exactly the same distances that we saw in here in the Mahalanobis distance. So just to show you, right, that learning a Mahalanobis distance or learning any kind of, the distance directly with the M is the same thing as learning the transformation. Any questions up to this point? Yeah, it is pretty awesome. Thanks, Dennis. It is quite cool. So let's keep diving. So indeed, when we talk now about metric learning, we understand that it's not about learning a distance; it's about learning a transformation. And when we talk about learning a transformation, and you can go to metric learning from all kind of directions. So we took it, through the Mahalanobis, but you can think about this also from kernels or looking into other kind of functions. But what we're really looking for is, given the original feature representation of the data, how finding a new representation that is easier to separate. And that's what I think you see here. So you start with, let's say, a mixed setup. You separate that so that the new representation, it's easier to separate from a semantic point of view. We just showed now a linear transformation, basically using L, but already big data, neural nets. You could also do some nonlinear transformation as well. In my when I did my studies, we did this nonlinear transformation with gradient boosted regression trees as well. So this can work also with any nonlinear function as well. And there is this work by I think Chang Ka-Vu, who works in Microsoft. He did an excellent survey on different kind of approaches. Do check it out. I see the question, do I understand correctly that the space transformation can instead be represented as distance function, a gain of explainability? I think it's the other way around. So basically, like the distance is represented as, instead of representing the distance, you're learning a new representation where the Euclidean distance makes sense. But do you wonder if it's possible to do it the other way around? I don't know. I need to think about this, and maybe talk to me in the Gather afterwards. Yeah, let's talk about this afterwards. So let's understand in a second, what does this mean? Like basically this new representation, because learning a new representation sounds awfully like manifold learning. So for those of you who are familiar with manifold learning, it's basically, trying to reduce the dimensionality, but in a way that preserves the local distances between nodes. So if, let's say, you have in the higher dimensional space this point close to this one, then in the lower dimensional space, these points will stay close. And indeed, there is a little bit of a similarity. The difference here is in the supervision, really. So I'm reducing the set again, apologies for my attention. So the difference is in the supervision. In metric learning, you're using the supervision and you're using the information you have about the classes to learn this new lower dimensional representation. So you're trying to learn a representation, let's say in this case, of an algorithm that we'll dive into in a second. You're learning so that a representation that these points end up being closer together, while these points further away from this one. Where if you would use manifold learning for this activity, all of these points will roughly be in the same place. And just to maybe kind of showcase, because I think UMAP has a very nice demo on the differences. So UMAP is an both manifold learning solution, but they have also a metric learning solution, and they apply this on MNIST, but the MNIST fashion, which is basically 10 classes, same amount of instances, but of fashion. Which is a bit harder of a problem. Like, I don't know, the difference between a cert and a pullover isn't as clear as between a 7 and an 8. And what you see here is you really see the difference between manifold learning and distance metric learning, where when you apply manifold learning, similar classes are still remaining similar, whereas when you do distance metric learning, there is a clear attempt to separate between those classes based on the information that they're providing. We will solve this also in the case that we're showcasing. Yeah, so I think transformations are often optimized and evaluated on neighborhoods. And I think here we're starting to dive a little bit into how does the supervision look like for metric learning, and in what way does it differ from classification? Because in classification, you're basically having a function that generates a prediction, a classification or regression, right? It generates a prediction, and then you are doing some sort of a loss based on how do this prediction differ from the expected value that you've had, from the actual value, basically. In metric learning, the output you get isn't a prediction. The output that you get is a new representation of your data. And what you're trying to do is you're trying to get a loss function where it represents which of those instances are, let's say, instances that are closer together or should be closer together. Are they actually closer together? And instances that should be further apart, are they actually further apart? Let's dive into the notebook once more, just to kind of give you an example on this. Actually, before diving into this, maybe I'll go to this slide. The supervision when it comes to metric learning can also be a little bit different, and sometimes we call it weakly supervised than the regular class supervision. So, of course, you could use labels. Basically, for every instance, if they are the same label, they need to be closer together. If they're different labels, they can be further apart. But you could also give different types of information. It doesn't have to be labeled. And in fact, not all of your data has to be fully labeled. So, for example, in this case, right, like when we talk about tuples, it usually comes in two sets. So you could have sets of points A and B where A is similar to B. So I don't know, king and queen, cheesecake and tiramisu, let's say, those need to be close together in, let's say, a word domain, where points that are further apart, I don't know, king and boiler, right, needs to be further away. You could also have triplets, and that's if you've ever heard of triplet loss. That's very common in this field of metric learning, where you basically pick 3 points, let's say an anchor, and then 2 other points that one is supposed to be close and the other one's supposed to be further away. So you can think about, let's say, king needs to be closer to queen than to a toaster, right? And then you can look into the embeddings of these words, and this will be the guidance you give it. And quadruplets, that's, I think, a bit less common, but still apparent, where you give 4 points, where A is closer to B, then C is closer to D. So stuff like king is closer to queen, then toaster is to wife. Yeah, and then now that we sort of understand that supervision doesn't necessarily has to come from labels, but it can also come from different sources, we can dive back into this notebook example, and to showcase, I think, one of the let's say one of the loss functions that I like the most, and I think it's very resemblance to a different loss function I'm going to show you later, but it I think stemmed a bit earlier than that. And that's called the large margin nearest neighbors. I think it was brought forward by Weinberger and Sol in 2005. When you look into this function, it looks a little bit like this. So it has 2 parts. This first part, right, is you are looking into points that have the same label or should be in the same neighborhood. And you're penalizing on the distance between them. So basically, if 2 points need to be neighbors of each other, but they are further away, let's say the distance is 3, then you're penalizing the square distance, which is, let's say, 9. So that encourages the algorithm to learn an L that brings those target neighbors closer together. The second part of that loss function is if there is an imposter, like let's say an entity that shouldn't be a part of the neighborhood. So if that instance is closer to my anchor than the J, than the actual neighbor that I need to have within some sort of large margin, and this one here doesn't matter that much because L can always scale. So yes, you just put 1 here and then L learns a transformation. What it does, it penalizes for imposters within the neighborhoods. So if you're looking, let's say, at this, right, the same transformation that we just shown, it will learn an L so that the Mahalanobis distance looks like this. So basically tries to find all of these instances that are similar to make them closer, while these instances that are further away, further apart. And you can see basically that when you analyze this function, you see a couple of things, right? You see that in this case, the transformation is linear. You could have used something that is nonlinear. The latent space that they're using here is Euclidean. So basically, we're trying to optimize the Euclidean distance between them. And the objective function, as I said, composed of pooling, pushing, and then some sort of trade-off. By default, the trade-off is the same. It's 0.5 between those 2 terms. Though you can best learn it with cross-validation as well. The reason why I'm detailing this, and by the way, there are a lot of really cool, I'd say, metric learning approaches. When you read metric learning papers, it's always about trying to find new ways of representing similarity within the neighborhood. Like neighborhood component analysis does some sort of a softmax and trying to improve the accuracy that your nearest neighbor is actually the one from the same label. ITML uses information theory topics. This paper is actually written by AI celebrities like Andrew Ng, Michael Jordan. It's a really cool read, and I think one of the first ones in this field that really introduces this topic of distance metric learning. So if you have some time and you're looking to see some historical, I know, instead of looking at the Michael Jordan basketball game from the 90s, you want to read a Michael Jordan paper from 2003, you can find it here. And the reason why I'm kind of diving into those, because as you will try yourself to read a little bit more onto these loss functions, you will see that here, you will see lots of different loss functions, right? But every time you read a loss function, you will find basically similar activities. Like you will find what is the distance that they're using here. Are they using, let's say, triplets or pairs? And what is the distance they end up using? So basically these concepts of understanding the output distance, understanding how does the supervision look like, and understand the objective. Like in this case, I think it's really similar to what we were just showing, right? The distance between the positive points needs to be small, and the distance between the negative points needs to be large. So understanding these as a concept, I think, is a good baseline for you to dive into. Okay, I think I talked enough. I think I'm ready to show you some cool examples in code. But first, I want to see if there are any more questions. So let me look into the Slack. I don't see any questions on Slack. Let's see questions on the. Let's see. How? Okay, let's start with. See a lot of questions. So UMAP or TSNE. They're actually different approaches, but you could use both of them. Both of them are useful techniques for manifold learning, and I think this paper really, this publication really nicely showcased the difference between them. Do check it out. How is a neighborhood defined? Good question. It's a parameter, so it's something that you could also learn in your either learn or provide yourself. Depends on how, let's say, how do you want to represent your data. We will showcase, I think, a couple of examples where we will have different case, and that translates to different sizes of neighborhoods. Let's see. You still need a definition. Definition of what? I'm sorry, but I got lost here. When one wishes to use triplet distance, are we talking about supervised problems, right? So in metric learning, they're all supervised information, right? It's just that the information that we are providing is coming in the form of triplets. So you can think about it this way, right? Let's say that you have a label, right? Like let's go back to the to this data set that we've had, okay? And you have these two images of a sneaker, right? You can create a triplet supervision by saying, well, this sneaker needs to be closer to this sneaker than to this coat. That creates basically a triplet representation of your supervision. Does that help to clarify? Oh, how do we decide in neighborhood? Good question. So if we say that our neighborhood, let's say, composes of, there are two ways of doing this, right? One is you can specify a distance. You can say that anything that is within, let's say, 0.1 is in my neighborhood. Another, which is, I think, a more natural way of doing this, is to look into your k nearest neighbors. So if you have, let's say, within your 5 neighbors, neighbors of the same label. So let's say all of your, for this instance, all of its neighbors are sneakers, then that's great. But if in your neighborhood you have coats and ankle boots and sandals, then that isn't so good, right? So the loss function, right, is determined by this K, right? Like based on defining who in your neighborhood is, sorry, how many instances are in your neighborhood. I think we will show this a bit in the code example, so you can dive a little bit into this later on. But if I didn't answer you, let me know. Devil's advocate, how does this relate to GAN? It is a form of representation learning. Definitely, it's not trying to, I guess, reconstruct it. But I think in this context, we are actually more, I think in GAN, it relates quite heavily, but I think in this context, we are looking for the representation itself rather than, let's say, the output of that network. So I think in GAN, it's more important to look into the transformation function. Here, you're mainly focusing on the output representation, but we can have that conversation, I think, also in the Gather town as well, or in Slack. But they are quite related. They're both forms of representation learning in a sense. Cool. Ready to see some fun code? Do people do classification on top of the learn metric, like k-nearest neighbor or cluster? Yes, you can definitely do that. In fact, in this new representation, the idea is that you have a lower dimension that represents your data in a manner that doing this sort of classification, clustering, k-nearest neighbors is much more simple and much more intuitive. But we will show this, I think, in a second. So let me show you a little bit on the of code. Oh, I see more questions. Maybe last one before we dive. How do you evaluate something like on this on a holdout set? It seems any learn metric here would be entirely based on the data you have in hand. Quite simply, actually. I didn't do it in this demo, but the way you do this is by taking, let's say, no, actually, we will show this on the test sets. Yeah, we do have test sets, so stay with me. But if you're asking about the validation, you can take, let's say, a validation instance and then evaluate that. You take the training points as your reference, and you will check whether, let's say, your test points after a transformation are close to known training points. But we will show this. I think this will be cool. I am muting the chat again. I'll be back to it in a second. All right, so let's dive into this data set, which I found to be really cool. It's a data set called Banking 77. It was made available by Inigo Casanueva, Tadas Temkinas, Daniela Hertz, Matteo Anderson, and Ilan Vulic. And I apologize if I butchered any of their names. But it is a very fun data set. It comprises of 13,000 customer service queries labeled into 77 intents in the banking domain. So you can load this data from here. They made this available. And you can see a couple of examples. So they have, I think, about 10,000 training instances and about 3,000 test instances. And you can see that you have, let's say, a category that is change PIN, and then there is the text associated. Like, is it possible for me to change my PIN? Top-up failed, quite clear. I think in the banking domain, it's quite relatable, and I think you will be able to understand what happens here. To make this problem a bit more feasible also for your notebook, I am reducing the number of training points that I'm going to use. So I'm only using 10 training points, only 10, from each of the 77 classes. So in total, we will have 770 training points, but I'm not touching the test. So I'll still use all the tests for evaluation purposes. In their paper, by the way, they also showcase results for if you take 10 classes from each, 30 classes from each, or if you use all the data set. All right, so we started from raw text. And the first thing we need to do, I think, before we start with any metric learning, is we're going to have to start representing this in some sort of a vector, right? Now, this talk isn't about sentence embedding, but if you're interested in this problem, you have links in this notebook as well. And as a simple data scientist, what I'm trying to do, I'm trying to get to a good representation. I'm looking into, well, what are the, let's say, best supported models, right? So these are all the transformation models. Let's say I look into the evaluation. They have this really nice Excel or Google Sheets, seeing, wow, okay, this looks like it's the best sentence embedding that they have at the moment. So this is what I'm taking. And it's quite straightforward. You basically load the sentence transformer on this device. If you're running this, by the way, this encoding on a CPU, it might take about 4 to 8 minutes. On GPUs, it's rather fast. And what we get ultimately is this kind of set. So we have a training set which has 768 features. The class associated with each of those points. And then we have the test set, right, which is the full data set also with this embedding model and the 3,000 labels. Next, let's start evaluating these embeddings. There will be two ways that we will evaluate the embeddings, and I want to kind of showcase both of them. The first one is a visual one, which I find to be quite cool. And for that, I use a library called Altair. It's, I think, the way they described it is a descriptive visual, interactive visual component on top of notebooks. It's really quite easy. So if you're looking for something interactive on notebooks, do check it out. I will share, I think I put the links on it in the notebook as well. The idea behind it, well, another thing that I like, which also saves me right now because my kernel died, is that they actually embed these visuals within the notebooks themselves, so it's remain available for you even if you don't have a kernel. And what I do here is I basically take these embeddings that we learned from the sentence embedding and doing a PCA transformation on them. And what we see is this very, very colorful image that really doesn't tell you much. And the reason why it doesn't tell you much is because it's PCA. That's exactly the reason why you sometimes want to use manifold learning, because PCA isn't a good technique to visualize the relationship in a very high dimensional space. So what you want to do, yeah, thanks Ana Rosa. She put on the Slack the link to Altair. What you want to do, right, in this setup is to actually do something like TSNE or UMAP, so that you'll be able to see the relationship between the instances in the higher dimensional space. So that's what we do. And by the way, in I think TSNE, in scikit-learn 1, there is a new function which is learning rate auto, which I think is a better representation of the data. So what we do here is we took the query, we did sentence embedding, and then we did TSNE. And now we can see some things. Okay, now what do we see here? We see a couple of, let's say, categories that are very well separated by the general language model. Like, for example, edit personal detail. Right, I put here both the testing and the training points, so you could see them. And we see that, let's say, some instances are a bit, let's say, closer. Like, I don't know, changing pins is close to getting physical card, which needs to be activated by pin, or pin blocked, right? Or this one, which is a little bit all over the place, like why verify identity, verify my identity, and unable to verify identity. And we also see some that are a bit more of a mess, right? But it's a good place to start. I mean, if you think about, let's say, what we'll try to do now is to get a bit more of a, we saw a qualitative estimation, now we'll do a quantitative one. And we will use two measurements here, both the accuracy, we will do k nearest neighbor accuracy, but we'll also use the mean average precision, R, which is, I think, written by the same person that made this, this library available. His name is Kevin Musgrave. Again, apologies, Kevin, if I'm butchering your name, but I really appreciate the work you've been doing. And what I want to show here is basically an example on how does this parameter evaluated, right? So basically, if you have 10 results, but only the first one is correct, then that's good. But if you have, let's say, only the first and the 10th is correct, it means less whether if, let's say, the first and the second neighbor is correct. So what we were going to do is we're going to rank all of the neighbors for each point, and then we'll see if, whether this neighbor, the first, the second, the third, the fourth, are that same of that same label, basically. Let's go back to here. And what we see here in that baseline is that we actually have a decent accuracy, which is, you know, kudos to the language model, right, to the sentence embedding and BERT. I see someone had an import error. I mentioned that in the Slack beforehand. Just restart the kernel. Yeah, thanks, Claudia. What you see here is basically the accuracy is quite decent. Still not at the level that the paper is reaching to. But let's say the neighborhood itself, right, especially as you grow to higher neighborhoods, you have much less precision here. Okay. So now let's do some metric learning. So we saw large margin nearest neighbor. There is this library here called metric-learn, which already implements quite a lot of these metric learning functions. And you can experiment and read a little bit more about the different offerings that this library already has. But it's quite straightforward. So you put large margin nearest neighbor, you put here number of components. So basically that will be the output dimension that you would want for your transformation. So in this case, we will learn a 768 over 192 matrix. You specify k equals 5 in this case. So basically, when you are evaluating the neighborhoods, always look into your 5 k nearest neighbors. And you do fit. And frankly, you know, like if I'm thinking about my talk, this would have been it, right? Like these 4 lines, that's what you need to do for metric learning. I specified here verbose true, so we can see what happens here. So basically, this is the objective function of the element n. And this one is the active constraint. So basically, how many imposters are within the neighborhood? And what you see is that as it learns, the number of imposters keeps going down. So it's able to find a representation where those neighborhoods become less and less corrupted and more homogeneous. Ultimately, you can just do transform of that original data set. And then you get both a much better accuracy, and we evaluated it for different k values, 1, 3, 5, 7, 9, but also much better, let's say, neighborhoods. And when you look into the output visually, it's a bit tricky, but let me try to put this like this. And maybe, of course it doesn't. I'll try to put them side by side, so you'll be able to see this, this comparison. But I think you will see that this one is a much cleaner representation, or a much clearer transformation. Yeah, so that was the original one. And there you see you're really able to address some of those, let's say, more wacky and noisy transformations and breaking them down into classes. Yeah, another thing that I think worth to kind of showcase, right, especially with this tool, right, is like how easy it is to explore and evaluate your data sets, right? So like if this is, let's say, Visa or MasterCard, and this is a wrong labeled identification, yeah, this is actually a true, false, negative, but I want to show a couple like this one. This is about cancel transaction. This is a cluster on cancel transactions. And then you have this one, which is request refund. How do I cancel previous purchase? Which, to be fair, is very, very close to cancel transaction, right? How do I cancel my order? So it actually, is able to take into account also proximity of classes in this representation. And again, maybe one last point, right? We didn't use a lot of data. We only used 10 points per every class. And still, like we were able to find a meaningful representation. Maybe one last point that I wanted to mention before diving into the deep learning ones is about the dimensionality reduction. So we reduced the dimensionality from 768 dimensions to 192, about a quarter. And now, frankly, this is just a magic number. You would probably want to do a validation and to evaluate if that is sufficient for you. But the guiding principle here is that the 768 dimensions, that was to encapsulate the wider general language model, right, for all kind of text in the entire world. But in our case, we're really just trying to learn a specific problem, which was trying to categorize and classify customer service queries to maybe later a chatbot to answer those questions. And that's why using a lower dimension makes a lot of sense. And again, looking into what is the actual value that works for you is something for you to dive into. For the last part of this tutorial, maybe let's just see if there's any questions, or you know what, I'll go through the last ones because I want to make sure that people who wants to try out also with deep metric learning will be able to do so. And then I'll use the rest of the time for questions. So as I said, you can't really do metric learning without deep learning, right? And it's the biggest thing now. There is this really great library, again, that Kevin made available, and you can read about this in the library website. I'm not going to dive into, here I use TensorFlow, sorry, I use PyTorch. I'm not going to give a tutorial about building a deep learning model in PyTorch, but I will highlight a couple of differences with respect to what are the things that we are specifying in order to make this work. First, regarding the model. So the model looks, I think, similar to other kind of deep learning models that you will show. So it's basically, let's say, a hidden layer here, then another hidden layer. But the output, instead of, let's say, outputting it with one activation function, which is, let's say, the regression result or the class that we're trying to learn, it's actually just another one of those linear representation, or basically we're trying to optimize this 192 features. And that will be the output representation for us. This is the full model. There is nothing more to it. We need to specify here a couple of functions. So as I said, what is the distance that we're going to use to evaluate the, let's say, the differences between the embeddings? What is the loss function? So in this case, I'm using a contrastive loss, which we showcased also before. And what is the mining function, which basically helps me to find out which are the neighbors that I'm every time going to evaluate. So I think in this case, in an angular miner, is trying to find out neighbors that are similar in angle, or I think you can see it in, I open again that library website. And what's really nice about the work that, that Kevin has done here, that when you look into the losses, it really details you what is the setup that it works. So, you know, what is the reducer that that he's using, what kind of, sorry, what is the input for that reducer, and how do you, you know, how do you create a fit that actually makes this this work best if you're using the LP distance or the crossing distance. In this case, I chose the L2 distance and the same kind of output dimension, just because I wanted to compare this with the linear transformation. But you can play around with these settings as well with this this model. And the last point that I think is a little bit different is these parts. So usually what you do when you're training every epoch, you are putting your data in labels, you're doing optimize zero grad. But this one is a little bit unique in a sense that first you're creating your embeddings. You basically apply your model on your data to get a new transformation. You are using the mining functions to learn basically the tuples. So which of the instances needs to be close to each other and which ones needs to be further away. And then you feed this into the loss function. And that's the thing that you're doing backward and an optimization step. That's really the core of it. And there is, I think, some good example code in the library information. What you see here is basically the loss keeps going down, and ultimately, right, you're getting the same embeddings by applying the deep metric learning on the data set. And then you're using those embeddings in the same way that we've done here. So basically evaluating the mean average precision at R and evaluating their accuracy. And using the same information to visualize this. Now, what I found interesting looking into the output from the deep learning one is that you see it's much more separatable than the linear one. And part of it is because when you're applying non-linear transformation, it's much easier to kind of separate your data. It doesn't necessarily has to translate to better performance, but in this case it is. And like I said, the way that you would probably want to build this is with a proper validation set and making sure that, let's say, you find the hyperparameters that optimize the, let's say, the error that you're looking at. So if I just go back again to the original objectives that I had for the talk, we learned a little bit about metrics, distance functions, and metric learning. I think we saw what it means to learn a distance, and then we completely forgot about it. Instead of that, we decided to learn a transformation. We saw the relationship between metric learning and manifold learning. We got a chance to dive into some loss functions and understand that basically we're evaluating the representation. And we saw a really, really cool data set and seeing, you know, like how do you actually apply this in practice to learn about segments in your answers. And I hope you guys had fun too. So I think with that, we have some time for questions. Yeah, clusters are much tighter indeed, right? That's because it's easier to separate. When you look into the definition of the contrastive loss, you can also specify here what is the positive margin and what is the negative margin. So if you want, let's say, to be more tight, you make this really, really close to 0. If you want to make this a bit wider, you increase that positive margin. Is it safe to say that the nice results shown here are due to fairly clean data? I don't know. I don't think so. What I was trying to showcase actually is that there is quite a lot of overlap between the classes themselves, right? So if I go again to the, maybe here, right? Maybe before the actual transformation, right? This is how it started after using the state-of-the-art sentence embedding, right? Sentence embedding, sentence transformer Siamese BERT. And even there, right, you see like, I know, disposable card limits, disposable virtual cards, get virtual cards, virtual card not working, right? These classes are really, really close together. And there is quite a lot of also mislabeled information. That's what I was sort of trying to showcase as well, right? So I can't say it's all just, let's say, due to clean data. I think part of it is really about, let's say, the approach as well. Let's see more questions. If we apply our model to a new set of customer service text without labels, can we expect to see new clusters for new previously unknown classes? I believe so, right? Like what we've done, what we're doing in our work setting, we're using this actually on companies' behavior, trying to detect new types of companies' behaviors and seeing how they differ from each other. One thing I didn't mention, but one key strength of this approach is that it works with very few labeled instances as well. So if you, let's say, only have, I don't know, 100 points labeled out of a database of 10,000, especially when you do linear transformation, it generalizes really well. Yeah, I see there are questions on the Slack channel as well. Can you explain why n components is 192? What happens if n components is 2 and visualize directly? Very, very good question, Nicola. By the way, I'll go to the Slack questions in a second. So what we've done in the, I'm not sure what it will do in the nonlinear one, but I know what it will do in the linear one, and that it will give you something similar to this. And the reason is that finding a linear transformation that shows that representation that we've seen to a two-dimensional space directly is really infeasible, right? So the reason why TSNE was able to kind of identify those neighborhoods is because when they transform, they're using a non-linear dimensionality reduction approach. And if you're, in a sense, PCA, right, it's also a linear transformation, right? It just tries to maximize over the variance. So you will get something similar to this. I don't think I tried doing this directly on the two-dimensional space. My suspicion is that it's going to be still noisy because, but you know, try it out. Definitely in the deep one, let's say. In the linear one, I can tell you already, it's just going to translate to this thing. Let's see. What are the roles for reducers and minors? Okay, so minors, as I said, right, it's really about trying to find out how do you create these sort of tuples based on the function that you're looking? So how do you create pairs? How do you create triplets? How do you create quadruplets? Reducers, I think it's about taking all of these losses from each individual output and generate one loss function. So basically you are creating, if we look at, let's say again, one of those losses, like the contract loss. If you're looking into this loss, right? So this loss is defined per every anchor point. And I think the reducer, what it does is just basically aggregates them all together to, in this case, an average one, an average non-zero reducer. So things that are, let's say, if they are 0, they don't count into the average. But I think this flow should make it a bit clear, right? So I hope that answered the question, Victor. Let's see. I wonder if you could use this for unsupervised outlier detection. We talked about this before, right? When we talked about the Mahalanobis distance, that this is an unsupervised learning approach. In a sense, you got, you came to a metric learning talk and you got an outlier detection technique for free. So that's value for money. But I think that in order, as I said, to do this, let me just go back to the PCA whitening. Yeah, this one. This is really helpful for, let's say, outlier detection, right? Like this is something that can really, you just look into the distance between the mean, and then that helps you to detect outliers. But the metric learning itself requires some sort of supervision. And again, it doesn't have to be full supervision. It could be weak supervision. It could be partial supervision even. It doesn't have to be for all the points. How many people label triplets in practice? You can think about this. You can think about this sometimes as part of the data engineering activities that you do. Like, so number one, the fact that a loss function is defined by triplets doesn't mean that your data has to be triplets. We just saw it in this example, right? Where our data were classes, and then we were able to apply a triplet function on it. The second point is that you can think about it sometimes like if you are Netflix, right? And you see how many minutes someone spent on a specific show, and you can say, well, like this show is closer to a different show that another person spent a lot of time of, as opposed to this third show that he watched just one episode and didn't find interesting at all. So it's really about, how is it represented in the world? But I think that think about it more of a flexibility point rather than as a limiting factor, right? So if your data is such that this is the kind of supervision you have, that's great. Otherwise, you can use the label. Thanks, Luis. I appreciate that. Thanks, thank you, Eyal, as well. I liked your talk as well. Can we talk about multimodal case? Ooh, interesting. There are different ways of kind of generalizing this this activity as well. So if you read the literature, you could find what they called locally linear metric learning. So basically, you're trying to learn different transformations for different areas of the space. That is actually something that is useful. So you first try to split your space and then learn different transformations on each area. Sometimes you try to do a linear transformation and then go non-linear to kind of build on top of those similarities that you've already done. But frankly, in most of the applications that I see recently, like the deep learning ones, they're just trying to directly do this sort of learning. All right, I think we can wrap it up. So as mentioned before, I'm going now to the where is it? Yeah, I'm going to the Gavertam to keep having this conversation if anyone's interested in following up. It can be about metric learning and its application. It could be about banking, IT, it could be about board games. I'll be very happy to get more recommendations. My wife and I have a collection of, I think, 250 of them. So your advice would surely be appreciated. And looking forward to seeing you again in person next time.